very redundant topic. All of you who have joined today have been working with cochlear implants and have vast amount of experience. So signal processing seems to be a very basic part of the whole process. So, but in a way, somehow this part is a bit heavy on technicalities, and sometimes it is a little bit difficult for us to understand, especially when there are so many manufacturers that we work with, and everybody is working on different principles. So our group, especially today, decided to take this challenge heads on and dive into this topic and try to figure out how much we know, and we'll take it as a discussion, and I hope all the experienced professionals over here will be able to give their inputs as well. Apologies for any mistakes or anything that I have made in the discussion. So without delaying it any further, let's start. So when we talk about signal processing in cochlear implants, on the surface, the basic thing that a cochlear implant does is it represents acoustic information, speech information in the form of electrical pulses. Okay, that's the basic thing that a cochlear implant does. But in this process, there are multiple steps which are involved, as we all know. So when an acoustic signal or let's say a speech signal arrives at the processor of the cochlear implant, it is picked up by at the microphone level. The microphones convert it into electrical signal and send it for front-end processing. Now, when we say front-end processing, these are certain basic manipulations that the processor's electronics will do to the signal. The main goal over here is to improve the signal to noise ratio. So at the front-end processing, we have certain things like the automatic gain control, AGC. All the audiologists over here, they are familiar with it. It's a fast-acting process which basically works to compress instantaneous loud noises. And at the same time, there are automatic sensitivity control. There are different terminologies that different manufacturers use for this, but it basically manipulates or shifts the input dynamic range of the processor's microphone in order to provide the best signal to noise ratio, to provide the signal component with the least amount of background noise. Once the signal goes through these front-end processing, it is sent to the filter bank. So in the filter bank, the signal is divided into its component frequencies. Okay, so there are different bands of frequency where the signal is sent through. And again, at the level of the filter bank, also there are the processor or the signal undergoes several manipulations or processing. After this band pass filtered signal is sampled and selected, and we'll talk about this further when we go ahead in detail. It is amplitude mapped. It is compressed to fit the electrical dynamic range of the individual. And then it is sent to the RF encoder, which converts it into radio frequency signal so that the external coil is able to send it to the internal coil. And at the level of the receiver stimulator of the implant, it is converted into electrical pulses and sent to the electrode array for further stimulation. Now at this level, at the level of sampling and selection or the amplitude mapping is where our signal processing or the mapping function mainly comes into play. Okay, again, there are slight variations here and there across manufacturers. Now, before we start talking about signal processing, let's again go back to the basics and remind ourselves that when we talk about any sound, be it a simple sound like a pure tone or a complex speech sound, the three main characteristics that define it are its pitch characteristics, its loudness or intensity characteristics, and the timing or durational characteristics, right? And for a simple sound like a pure tone, it's a very simple linear relationship usually between pitch, loudness, and timing. Whereas when we talk about complex sounds like speech, there are a lot of overlaps, and there is a very sophisticated combination of all these factors which gives the sound its character. Um, Here there are a few ways that have been used to represent a sound visually for our understanding. Typically, it is represented. So the first, all the three pictures you see here represent the same sentence. The sun begins to rise. The first one here is a waveform representation. So a waveform representation is nothing but the amplitude fluctuation that happens over a duration of time. Okay. Next, you see the spectrogram. A spectrogram is a sort of a three-dimensional representation wherein all the three aspects, the durational aspect, the intensity aspect, and the frequency aspect are represented in the same graph. So in the x-axis, we can see frequencies increasing as we go up, and in the y-axis is the duration. Whereas the color intensity or the brightness of the color or the darkness of the color represents the intensity of the sound. So here we can see how the intensity of the sound shifts from one frequency to another across duration. Okay, so that's a spectrogram, and a simpler version of frequency or representation is the spectrum, where it just shows the energy concentration across different frequencies for a particular speech sound. And then at last is the envelope, which is basically the power function of the particular waveform over a period of time. Why we are talking about this will be a little clearer as we go ahead in the discussion. This will help us later in understanding a few of the speech coding strategies. Now, let's talk about how our normal cochlea codes these characteristics. Loudness coding in our cochlea, as we all know, depends on mainly the magnitude of the basilar membrane vibration or displacement. For a softer sound, the magnitude of displacement is usually smaller, so it stimulates a smaller number of hair cells and therefore a smaller number of neurons. Whereas for a louder sound, the displacement in the basilar membrane is much more, and hence it ends up stimulating a lot more of the hair cells and corresponding neural fibers. So as the number of stimulated hair cells or neurons increases, the loudness perception increases. So at the level of the cochlear implant, as we know, in a cochlear implant, we use electrical pulses. Mostly, in most of the manufacturers, they use biphasic pulses. So in an electrical pulse, we measure the overall charge, the amount of charge. That is what determines the loudness of a particular sound. So as we can see in the biphasic pulse, here we can see the current level or the amplitude of the pulse. As the amplitude increases, the current level increases. That increases the overall charge and thereby the loudness perceived. Another way of increasing the overall charge level is by increasing the duration of the pulse. Okay, horizontally, the duration of the pulse. Or we can increase both simultaneously, and that will again give us the perception of a louder sound. So as the amount of total charge increases, the perception of loudness increases because that ends up stimulating more number of nerve fibers. Also, to an extent, the stimulation rate also helps in coding loudness to an extent because of the loudness summation factor that happens at the level of the neurons. Coming to the pitch coding strategy, as we all know, in natural cochlea, there are two theories by which cochlea codes the pitch. One is the place theory and one is the rate theory or the volley theory. So the at lower frequencies, for lower frequency sounds, our auditory neurons are highly phase locked to the incoming stimulus, and they are able to fire at a rate which corresponds to the frequency of the incoming stimulus, and that is how they are able to code for frequencies. But this ability is limited to very lower frequency, generally below 1500 hertz. Above, for higher frequencies above 1500 hertz, our cochlea mainly depends on the site of stimulation. As we know, the basal part of the cochlea mainly is sensitive to higher frequencies, and as we go towards the apex, it is more sensitive to the lower frequencies. So both of these factors together code for pitch in a normal cochlea. In the cochlear implant as well, the electrode arrays in all the cochlear implants currently are designed in a way that each of the electrodes are assigned a particular band of frequencies, and generally the basal electrodes will code for the higher frequencies, and the apical electrode codes for the lower frequencies. So the three important parameters in the acoustic term, when we talk about frequency, electrically it is determined by the electrode selection, and perceptually that gives us the change in pitch or tone. Intensity is generally coded by total charge, and that gives us the perception of relative loudness. And the timing information is best uh, conveyed when we use a high rate of stimulation. When we use faster rate of stimulation, we are able to detect the minute changes in the stimulus characteristics over time, and that gives us the information about temporal characteristics of the sound. Now, talking about a cochlear implant, there are a few limitations, as we all are familiar. Uh, the first challenge in terms of pitch coding. Now we know that in our normal cochlea, we have thousands of hair cells, and the basilar membrane has a very each section of the basilar membrane has very sharp tuning curves, so they are able to represent a rich or a very rich spectrum of sound. Okay, the spectral resolution of a natural cochlea is very fine or very high, but we cannot think of a cochlear implant or an electrode array to have thousands of electrodes to mimic the natural cochlea. This job has to be done by a limited number of electrodes. I think the maximum number of intracochlear electrode is 22 by the cochlear medical devices. So the job of thousands of hair cells are now limited to 22 electrodes. So the tuning curves or the frequency bands allocated to each of these electrodes are usually much broader compared to the sharper tuning curves that a natural cochlea has. Okay, so that is one of the challenge that we need to overcome in a cochlear implant. In terms of loudness coding, um, as we know, in our natural cochlea or in our natural hearing system, we are able to hear a huge range of sounds, right from a leaf falling or a leaf rustling to a huge bomb blast, right? So the dynamic range that each of us have is generally hundreds of decibels, or sometimes even more than that. But when it comes to electrical hearing or electrical stimulation, um, the electrodes do not have the physiological properties that our outer hair cells, the electromotility of the outer hair cells, which is able to apply a adaptive compression function to the incoming sounds, and hence the loudness growth function at the level of the neurons is quite fast, and our electrical dynamic range is much more compressed compared to the acoustic dynamic range. So it comes down from hundreds of decibels to hardly about 35 to 40 current levels when it comes to electrical hearing. Okay, so these are a few challenges that needs to be considered, that has to be considered during sound processing through a cochlear implant. Okay, to describe the various signal coding parameters, we can group them in a way that they answer a few of our coding questions. First thing is how much current is to be delivered, okay, or how the current is to be delivered. How the current is to be delivered is determined by three things. One is the coding strategy itself. Second is the stimulation mode that we use, and then the stimulation rate that we use. Second is how much current do we deliver. How much current is again determined by the individual threshold and comfort levels. It is determined by the pulse width as well as the pulse or the stimulation rate. And the third question is what information or how this frequency information is delivered. And that is determined by the frequency bands which are available, the range of frequency which is being delivered by the cochlear implant, the frequency bands, how they are allocated at each of the for each of the electrodes, and the number of maximas or what kind of spectral peaks or frequency information we are extracting from the incoming signal. Okay, so we'll talk about this in a little more detail going forward. Before going into coding strategy, I would like to go through the other parameters so that it's easier for us to dive into the other data. So first, talking about the stimulation mode. Okay, so stimulation mode generally determines the active channel or the orientation of the active channel in a cochlear implant. So a channel in a cochlear implant is basically made up of the source of the electric current, which in most cases is at the level of the receiver stimulator, but in certain cases it could be one of the at the level of the electrodes themselves. Plus plus the active electrode. So active electrode is the site or the tissue, the target tissue where the current has to be delivered, and the ground electrode, that is where the current after stimulating the target area, this gets dissipated or leaves the stimulated region. Okay, so the stimulation mode determines the location of mainly the ground electrode in relation to the active electrode. Okay, there are three main types of stimulation mode: the monopolar mode, bipolar mode, and common ground mode. I think most of the manufacturers now they apply the monopolar mode, but for our understanding, we'll just quickly go through each of these. So in the monopolar mode of stimulation, um, the active electrode is one of the intracochlear electrode. Naturally, it has to be one of the intracochlear electrode, whereas the ground electrode is located outside the cochlea. Most of the time, it is located in the receiver stimulator area in the cochlea. In the cochlear medical device, the cochlear devices, nucleus devices, there is an additional ground electrode or a ball electrode which is stuck under the facial muscle, okay, temporalis muscle. So in the monopolar mode, the current travels after stimulating one of the intracochlear electrode, it travels outside the cochlea. Okay. Now, depending on which extracochlear ground electrode is used, it is termed as monopolar 1, monopolar 2, or generally when most of the time both of the electrodes are used, and that is termed as monopolar 1 plus 2. Okay. The advantage in case of main advantage of using a monopolar mode of stimulation is that the current travels a longer trajectory from one of the intracochlear electrodes to a ground electrode outside the cochlea. So it elicits or it is able to stimulate a larger group of nerve fibers in its trajectory, and that allows for a louder louder intensity perception with a smaller amount of current. So it is current efficient, and hence that is something that is being applied most commonly by most of the manufacturers. Next is the bipolar mode of stimulation. So bipolar mode of stimulation is when the active electrode and the ground electrode are both located inside the cochlea. Okay, so here the advantage is that it is able to provide a very specific stimulation. Very specific region in the cochlea can be stimulated without causing distortions or unwanted stimulation of the other electrode regions. Okay. Again, it does not always necessarily have to be adjacent electrodes. When the ground electrode and the extracochlear electrode are separated by an additional electrode in between, it's known as bipolar plus 1. There are two, it is separated by 2 electrodes, it's known as bipolar 2, and so on. So here the advantage, as I said, is the specificity of stimulation, but because the current is localized to a very specific area in the cochlea, it requires a large amount of current to create a comparable amount of loudness perception to monopolar mode of stimulation. So your overall threshold current levels will become very high, and sometimes it may become difficult to even achieve the comfort levels of current with the available amount of power. Okay, so it's not very energy efficient, and hence little difficult to apply. So a visual representation of the bipolar mode of stimulation. And then we have the common ground mode of stimulation, which is not something which is very practically used for speech stimulation as such. In common ground mode of stimulation, there is one active electrode or one active intracochlear electrode, and all the rest of the intracochlear electrode form a common ground electrode. All the rest of them act as a common ground. Okay, so this mode of stimulation is usually used as a diagnostic mode in the implant telemetry or impedance measurements. Using a common ground mode, we can get individual electrode status information. So, like short circuits can be detected using only the common ground mode of stimulation. So, hence it is used more for a diagnostic purpose rather than for stimulation purpose. Okay. So again, a visual representation of all the stimulation modes. Um, Next, coming to the channel rate. The channel rate, as the name itself suggests, is the rate at which biphasic current pulses are delivered to each of the channels. Okay. Um, as it will come to anyone's mind, if you now think about this stimulus envelope, right? If we use uh, if we use uh, a slower stimulation rate, which is only located at the dotted line as you see here, do you think we will be able? Do you think we will be able to represent this entire waveform correctly, or in its original form? We will be missing out a lot of information from the waveform. Okay, so when we use a faster rate of stimulation, the more of the durational variation or the overall waveform of the envelope of the stimulus can be represented with higher fidelity. Okay, so generally faster rate should uh, result in better temporal cues. But does that mean we can use unlimited high rates of stimulation? We cannot. The main limitations we have here is one thing is we have to consider the channel interaction. When we use very fast rate of stimulation, especially if we stimulate multiple electrodes simultaneously, it can cause a huge amount of distortion, right? Even when we use sequential mode of stimulation, if we are using a very fast rate, it may so happen that before the current in the stimulated electrode gets dissipated, the next electrode may get stimulated, and that may cause distorted perception. Okay, so there are studies where they have seen that the speech perception definitely increases with increase in rate, but it also depends on the number of active electrodes or number of electrodes used for stimulation. If the number of electrodes used for stimulation is very high, we have to use a lower rate of stimulation to prevent distortion. Okay. The second thing we have to consider is the neural refractory period. As we all know, usually after about 800 hertz or generally about 1500 hertz or so, our neurons, auditory nerve fiber neurons, go into their refractory period or they go into adaptation. So even if we are using very high stimulation rate, our nerve fibers will not be able to do a phase lock, give us a phase lock response. Um, Hence, again, we have some of we have to consider the neural refractory period when we're using a high stimulation rate. Pulse width, as described earlier, it is basically the duration of the electrical pulse, duration of each of the biphasic electrical pulse. As the pulse width increases, the amount of current delivered for that particular duration gets multiplied and the overall charge increases. So increasing the pulse width can give us louder perception, um, louder louder perceptions. But again, the pulse width that we use is limited by the channel rate. Again, we have to use a trade-off between the adequate amount of channel rate that we use and the pulse width that we use. Next is the current levels. Again, as we all understand, current levels determine how much current we are delivering at each of the electrode at a particular instant of time. During our mapping, we generally set the minimum current level that is required for a particular individual to get a perception of audible sound. And we also set the maximum current level that is that a person is able to listen to comfortably. Okay, so all of the information that the processor collects and that undergoes pre-processing gets compressed into this electrical dynamic range, which is set during our mapping. And this again, of course, as we all know, it's a dynamic characteristic. It will keep evolving as the person gets more and more experience with the cochlear implant. Now, going into the speech coding strategies per se. Again, before jumping straight into the speech coding strategies, I would like to take a step back and let's refresh our memories about the theories of how sound is produced and how we perceive sound. Okay, so according to the source filter theory of speech production, um, our vocal folds basically act as the source of energy or source of energy for speech production, right? So the vibration of our vocal folds gives rise to what is known as the glottal pulse, okay? And this glottal pulse repeats at a rate of the vibration of the vocal folds, which is inherent to each individual, and it is characterized by the fundamental frequency. Now, this glottal pulse, as it moves through our vocal tract, it undergoes a filtration effect, right? For example, now when I say the vowel oo, my tongue is lowered, my jaws are slightly apart, my lips are puckered. So the shape of my entire vocal tract, it has a filtration. It applies a filtration effect on this glottal pulse. Okay. Similarly, when I'm saying the vowel e, my tongue is closer to the roof, my lips are extended, my jaws are closer together. So that adds a different filter confirmation to the glottal pulse. So this filter effect that the vocal tract has, it gives rise to what are known as the common frequencies. And altogether, we get the product of the source and the filter effect. So for a voice sound or a vowel, we get a periodic sort of a waveform which has the common frequencies, but it repeats itself at a period which corresponds to the fundamental frequency. But for most of the consonants, we know that the air column, it comes across an obstruction in the vocal tract. It can be at the level of the lips. It can be at the level of the tongue near the teeth or at the back of our mouth. But it undergoes an obstruction which creates a aperiodicity in the air column. Okay, so most of the consonants will have a waveform which is aperiodic in nature. So now coming to speech perception, if we just broadly divide our all the speech sounds into just vowels and consonants, so vowels, which are periodic sounds, they are mainly characterized by their formant frequencies, their spectral characters. Okay, our auditory system is able to detect or discriminate between vowels based on their formant frequencies. Okay, whereas for consonants, our auditory system relies not on the frequency, not on any particular frequency or frequency characteristics, but how the energy moves from one frequency to another, or how it transitions across a period of time. So the transition or common transitions are what are important features for identification of consonants. So the temporal characteristics of a particular speech sound becomes important in order to identify consonants. So to understand speech, overall speech, both the spectral characteristics as well as the temporal characteristics play a very important role. And hence, this is something that all the speech coding strategies has to consider during development. So classically, I am not going very back in time, but classically the major speech coding strategies can be mainly divided into envelope coding strategies and feature extraction strategies. So an envelope coding strategy, as the name itself suggests, it mainly tries to depict the envelope of the sound with as much fidelity as possible. And in order to do that, as we discussed earlier, they apply high rates of stimulation. Okay, higher rate of stimulation will be able to mimic or depict a particular envelope with higher fidelity. So they are also known as rate coding strategies and rely on faster stimulation rates. Whereas feature extraction strategies rely more on extracting spectral information like the common frequencies or frequencies with highest energy peaks. Okay, so they're also known as peak picking or pitch coding strategies. Okay, um, so one of the envelope coding strategies, which even now is used in different modifications, modified versions, is the continuous interleaved sampling. Okay, so continuous interleaved sampling basically functions in a way that when the speech sound arrives, it undergoes bandpass filtering, and the envelope in each of the envelope in a fixed number of bands are selected. The electrical pulses are modulated based on the amplitudes of the envelope in those fixed bands, and the corresponding electrodes are stimulated in a non-simultaneous manner. Okay? So, as the name suggests, previous stimulation strategies usually relied on simultaneous simultaneous stimulation of the selected electrodes, but that caused a lot of channel interaction and distortion. So continuous interleave sampling overcame this challenge by using non-simultaneous or staggered stimulation technique. So here they again, like I said, a fixed number of filter banks or fixed number of electrodes are selected, and they are stimulated at a very high rate in a roving manner. Okay, this high stimulation rates allowed good temporal information, depiction of good temporal information, and that led to good consonant recognition. Okay, but it was also found that because of only a few fixed spectral bands were used, the bandwidth of the filter banks were usually larger, and again, it was not able to take advantage of the place coding of the electrodes in the cochlea. Okay, so that limited the depiction of the spectral information. Um, So this is an example of on your left there is the spectrogram of the word choice, and here we can see very clearly how smoothly the energy is transitioning from high frequency to the low frequency as we move from the consonants to vowels and back to the high frequency, high pitched consonants like. On the right is the electrodogram of the same word using the same strategy. Okay, here you can see the high rates which are used. So most of the transitions are picked up. However, during perception, because of only a few number of electrodes, a fixed number of electrodes are used, we don't know the spectral information that is being depicted may get limited. Next, in the feature extraction strategies, most of the nucleus device, I think, relied on the feature extraction strategies. The very earlier ones employed the F0, F2, the fundamental frequency in second format information that evolved later on into F0, F1, F2. So basically, what these strategies did were they believed in picking up the most important frequencies information from a incoming signal. Okay, so so sorry. Okay, so they like I said, they believed in picking up the most important frequency information from the incoming signal. Okay, gradually they realized just depicting the format and the F0 information was not sufficient. Employing or picking up more number of spectral peaks gave higher spectral information. Okay, because these strategies were able to give good amount of spectral information, it did resulted good vowel discrimination compared to the envelope coding strategy. However, because they mainly depended on stimulation of the electrodes or the corresponding electrodes on a sort of simultaneous manner, they could not use very high rate of stimulation, and that affected the consonant perception, okay, or the temporal resolution of the incoming sound. Now, going forward, we will be discussing about the various speech coding strategies that are used by the different manufacturers currently. And these are mostly, as we will see, they are mostly the modifications of the basic envelope coding or speech coding strategies with the help of newer advanced technology which is available now. Coming to cochlear medical devices, as I said, they have from the beginning they have relied more on the spectral coding or pitch coding strategy. One of the latest speech coding strategy that they use is a modification of the N of M strategy, or which is in case of cochlear, it is known as the spectral peak strategy. So in this strategy, instead of picking up only the frequency bands with energy peaks, what they did was the incoming sound signal was again divided into 20 filter banks, and out of those filter banks, they picked up the maximum between 6 to 12 maximum energy peaks. Okay, how it is different from the spectral peaks is that if you can see the filtered waveform over here, we can see probably 1, 2, 3, 4, 5, about 5 spectral peaks. Whereas in peak strategy, we can see that even in a single spectral peak, we can find uh, energy peaks, 2 to 3 energy peaks. Okay, so the highest energy peaks in the filtered waveforms are picked up. So about 6 to 12 filter banks with the highest amount of energy are picked up, and the corresponding electrodes are stimulated in a non-simultaneous manner. They so this is a combination of the spectral the earlier multi-peak strategy, sort of peak picking strategy, and the continuous interleaved sampling strategy. Okay, here also, however, they could use only a fixed stimulation rate of 250 pulses per second, and this was where they found limitations in depicting the temporal resolution. Now they use a variation of the spectral peak strategy, which is known as the advanced combination encoder. So how it is different from speak strategy is mainly it is able to they use a roving or a staggered manner of stimulation of electrodes, which allows them to use a very high stimulation rate compared to the speak strategy. So they can use a stimulation rate as high as up to 3,500 pulses per second. Um, and they use 22 filter banks. Okay, so the number of the rate of stimulation that they use depends or gets determined by the number of spectral maxima that they are picked up. Okay, the more the number of spectral maximas they use, the more the number of electrodes that they'll have to stimulate, and the lower the stimulation rate, and vice versa. Okay, so this is the electrodogram of the word similar as we had seen earlier for the word choice. Here, I believe it looks like the there is better spectral resolution. I think the temporal resolution is more or less similar to this strategy, but the spectral resolution is better or more smoother compared to the CIS strategy. So again, a few of the default parameters, which coding parameters that Cochlear generally uses. They use most commonly they use the monopolar mode of stimulation, monopolar 1+2 as default, but they also have the facility to use monopolar 1, monopolar 2, or bipolar mode of stimulation. Common ground is usually used as a diagnostic mode. Stimulation rate can vary from 250 pulses per second to up to 3,500 pulses per second, but as a default, they generally use about 900 pulses per second. The speech coding strategy currently used is the A strategy, but they also have the facility or have the option to use peak or CIS strategy. Pulse width again can be varied from 25 microseconds to about 400 microseconds, and again, this has to be correlated with the stimulation rate and the maxima that are used, and we have to use an optimal pulse width. So by default, they use 50 microsecond pulse width. Most of the electrodes, for the slim electrodes, they use about 37 microseconds of pulse width. And again, the maximas can vary from 1 to about 11 maximas, but by default, they use about 8 maximas. Going to advanced bionics. So advanced bionics from the beginning, they have been relying more on the envelope coding or rate coding strategy. So they believe that if the information or acoustic information can be um, sampled or can be delivered at a faster rate at the electrode, it can give a um, very good depiction of the acoustic envelope and lead to better speech perception. Okay, so current advanced bionics processors use the high-res 120, high-res fidelity 120 speech coding strategy. One of the striking characteristics that they have is the current steering technology that they have, and we'll be talking about it further. So they advanced bionics, they use 16 bandpass filters. So the incoming signal is divided into 16 bandpass filters, and it has 16 corresponding electrode contacts in the electrode array. But what additionally what they have is they have 16 independent current sources at the left at each of the electrodes. So the current source is not just located at the receiver stimulator package, but each of the electrode act as an independent current source. So what this allows them to do is what is known as current steering. So to understand current steering, it is nothing but when we are able to stimulate or provide the electrical current in two of the electrodes simultaneously, it can result in the perception of multiple pitch in between the two electrodes. Okay, for example, now this electrode 1, let's say it corresponds to a frequency band with a center frequency of 750 hertz, whereas the second electrodes corresponds to a frequency band with a center frequency of 1650 hertz. Okay, now if we are stimulating or providing the entire current to the first electrode, it will result in a pitch perception correlating to 750 hertz. If we are providing the entire current to the second electrode, it will give us a percept of about 1650 hertz. But if we divide the current and send 80% of the current to the second electrode and 20% to the first electrode, it will result in a perception of intermediate pitch, which is closer to the second electrode, let's say about 1100 hertz. Similarly, if 60% of the current goes to the first electrode and 40% to the second electrode, it will result in intermediate pitch closer to the first electrode, about around 950 hertz. Okay, so this current steering technology allows each of these electrode pairs to have about 8 virtual channels in between them. Okay, so each channel does not correspond to each electrode does not correspond to a single channel, but it also has 8 virtual channels in between each of the electrode pairs. So they have about 15 electrode pairs, and between each of the 15 electrode pairs, with the help of the current steering technology, they have about 8 virtual channels. So altogether, advanced bionics claims to have about 120 virtual channels. Okay, so having this high number of channels and using a sequential mode of stimulation, they are able to use stimulation rates which are very high, up to about 5,800 pulses per second, using the high-res P stimulation strategy. High-res P is when they use the paired electrode mode, and high-res S is when they are stimulating single electrode sequentially. Okay, so if they're using only the 16 electrode channels individually, they can have a stimulation rate as high as up to 2,900 pulses per second per channel. And when they use the paired mode, they can have as stimulation rates as high as 5,800 pulses per second. So advanced bionics also commonly use the monopolar mode of stimulation. In high-res P, they use the pair stimulation. So the current is delivered to a pair of electrodes simultaneously. And in high-risk S, they use a normal sequential mode of stimulation. Okay, so they have the high-risk S, high-risk P. They also have a modified version of CIS strategy available. The pulse widths generally vary from about 10.8 microseconds to about 229 microseconds. So you generally use smaller pulse widths during the mapping schedule as well. They start with the smallest pulse width, and it automatically the pulse width increases with the change in to maintain a constant amount of charge. Coming to MEDAL now, MEDAL have used both the N out of M strategies or the peak picking strategies and also the CIS strategies. But their main principle has been based on replicating the fine structure of the speech sound. So the difference between the envelope and the fine structure is that if you look at the red line over here, the envelope represents the overall energy peak, so the power function of the acoustic signal over time. Whereas the fine structure, it also depicts the peaks and the troughs, not just the peaks, energy peak, but also the dips or the troughs in the signal. So this peaks and troughs are this temporal fine structure is a very important cue or a very important spectral cue, especially at the lower frequencies where the neurons auditory neurons are able to fire at the phase locked manner to the incoming signal. Okay, but most of these strategies that we have discussed so far try to focus more on the envelope of the signal rather than the fine structure. So what MEDAL does in order to replicate the fine structure of the um, speech envelope speech sound is they use a variable rate coding strategy. So what they do is in their apical channel, um, they use something known as the channel specific sampling sequence. So this channel specific sampling sequence, what it does is it generates a stimulus burst every time the signal crosses every time there is a positive zero crossing of the signal. So if I have to show you, for example, in this signal, every time the curve has a zero crossing, a positive zero crossing, a stimulus burst will be generated. Okay, so um, this way of generating pulses enables um, enables us to depict the fine structure of the uh, signal, and this is done mostly for in the apical electrodes in the lower frequency region up to about 950 hertz, and above that they use a general high rate sequential stimulation strategy, which is known as the HT-CIS. Okay. They also use the lower limit of the frequency range that they depict. The lower limit is generally for in most of the cases it starts from around 200 to 250 hertz to about 8,500 hertz. MEDAL depicts signals from about 100 hertz, as they believe that will lead to better fundamental frequency representation. Okay. The remaining electrodes or the more of the apical electrodes, the HTC strategy is used, which is again based on the CIS strategy. So here they have 12 paired electrode contacts, okay, which and each pair of the electrode contacts are supposed to have independent current sources. Okay, so they use a bell-shaped band-pass filter for each of the filter banks that allows slightly overlapping frequency response, which in turn allows them to have intermediate pitch perception. Okay, so this independent current sources and the intermediate pitch perception, it allows them to have about 250 virtual channels. This is what MEDAL strategies claim. And because MEDAL has longer electrodes, which goes more electrode arrays, which goes deeper into the apical region of the cochlea, and they have lesser number of electrodes. They have about only 12 electrode contacts. So the inter electrode spacing is much higher compared to both cochlear electrodes as well as AV electrodes, and that also allows them to have higher stimulation rate with reduced chances of channel interaction. So they can have stimulation rates as high as up to 4,225 pulses per second and pulse width varies from about 2.1 microseconds to about 425 microseconds. So these are the speech coding strategies which is employed by the manufacturers these days. I could not get much information on the Digisonic processors. I did try to search literature, but I did not get any ideas, and I'm hoping I can get inputs from more of the experienced professionals over here. So for us as professionals, it's a little hard to say which processing strategy is better than the other. At the end of the day, our brain is adaptive and it adapts to the signal that is being provided to it. So I think at the end of the day, the experience that the listener has with the cochlear implant and the amount of stimulation that they get, it sort of weighs heavier than the exact stimulation strategies that is being used. So here is a final representation of the vowel R. This is its spectrogram, and this is a rough representation of its electrodograms using various stimulation strategies. A, this is using cis, this is using high-res 120, and this is using the fine structure processing. So again, we can see certain some of the strategies seems to give better spectral resolutions, whereas others rely more on the temporal resolution. And most of them now try to combine both of this information with as much efficiency as possible. So this is all I had for you today. Would like to invite everyone to join in for discussions, any questions that you may have or any inputs that you may have for us. Thank you.
Thanks, Vaika, for your elaborative talk. Most of the things as a surgeons, it's beyond our what I can say. But I think Sandan is here, the best person. Vishwasa is also here, I have seen. So they can have a share few words regarding. But before going to, but yeah, how will you know you have a different strategy by adopted by different company? But how will you know that this is the best? Because we generally don't discuss this, this at this level. So how will you know which one is best? Do you have any reference? Kind of thing. It's the why we don't discuss.
It's hard to say.
Discuss all this kind of strategies. This is a, because if you go for all these 3 company implant or 4 company implant, but these things we should also discuss. I don't know. Maybe we are new. That's why we don't discuss. But
so most of the studies which are available, they compare they compare the different speech coding strategies that they have, or like the previous speech coding strategies they have versus the recent ones they have. Okay, so like for example, there are papers which discuss how some of the recipients performed with cis strategy used in middle and the FSP strategy used in middle. But again, the strategies are still within the same implant company. Right, we have comparisons between the speak strategy, the cis strategy, and a strategy in Cochlear, but it is within the same manufacturer. I could not find many studies which compare the speech performance across different manufacturers using different strategies. And it is a little difficult also because again, like the patient profile varies, everything, there are a lot of variation, the cochlear implant, the design, all of that. I think that is one of the limitations. So as users, it's a little difficult for us to say based on these informations only that which one is the best.
Yeah. Chandan?
Sir would be able to tell you.
Anybody, if you want to share?
Yeah, as Pragya was saying, most of the comparisons made are based on the same implant users, and that's what is possible if we do a control. But then there are studies wherein the average speech understanding scores are available, and speech understanding scores are compared based on group mean scores. What it means is these scores are definitely dependent on a lot of factors, and as long as the average scores are within a particular range, probably everything works well when your human efforts are combined with the things that the speech coding strategies give you. Like when we go for high instrumental information, the tendency is
Then your voice is
You're
breaking.
breaking.
when we give information on
Your
code
voice is
the
breaking.
speech too well or too less, there are okay better. Okay, now what we kept hearing is that the speech coding strategies, this seeing middle users in noise performance are also quite good. So instead of going exactly by parameter, we need to see the overall performances of these users in a group scores. If we find it in group scores, I know the statisticians will keep saying that group scores are not very reliable and they don't control every parameter. We need to understand that what works for making the person's speech understanding better, and that way most of the strategies that are used by the different companies are giving you enough speech understanding. But the present day competitions or present day query is not only speech understanding, but speech, the ease of understanding speech. What I mean to say is, with any of these companies speech processing strategies, users are now able to understand conversational speech quite well, even in presence of noise. But then the effort that they need to put to understand this speech is what is different, uh, depending on the amount of information that they are getting. And this is what we need to focus on, is ease of listening while using a particular strategy. Okay, so definitely when our technology is limited by not being able to do a controlled study on the same user using two different strategies, we have to depend on group mean scores of these studies. And if I do a, if we share our experiences of uh, doing a comparison, definitely the ACE-RE scores are much higher for speech in noise perceptions than other strategies. Pragya, am I right in saying that ACE-RE strategies are more in the scores, speech in noise scores are much higher? But then, does that mean that middle performers do not hear well in speech in noise? We have plenty of middle users who are doing well in the middle of the street. answering phone calls. Now, how is that happening then? Okay, so there must be some other informations that we are picking up, we are missing out on. So these are not very good studies. That there are not very good studies which compare across company
Across companies.
scores.
Right. Sir. I could not come across even I could not come across these group studies also. I think I'll have to look a little bit more. I could not come across any of the group data across the different companies' current speech coding strategies. And again, our experience with different manufacturers is slightly limited. We have used mostly Cochlear, so a little difficult for us to comment on it at the moment. So do you have any idea about the strategy used for Digisonic or Neuralink?
No, not at all. Just that, but I can share with you a person's phone number who can give you some information on this. Shibashish. He works for Oticon Medicals, but then I have tried to gain some information on that, but I have not been successful in getting it. Okay, but mostly they use the old N of M strategy.
NFM strategy.
That's what I understood. That's what I understood after talking to him, but nothing much to read on. So it is all based on conversation with him. It is N of M strategy. But their rate of stimulation is quite low. I don't know how, with such a low coding strategy speed, uh, they are still performing well. Here in India, what Digisonic implants that we see are actually old generation Digisonic implants. Oticon Medical Devices in US, they don't use these uh, processors or the implants at all. Yeah.
That's what Sandan, that during mapping and all this, what do you know that do you have in your mind that this strategy systems are there? This is they have adopted. So that means retrogradely, do you have in your mind when you do mapping and all these things? Are you getting my point? Suppose you are doing that.
Do you have to keep what strategy is being used while you are mapping? Yeah, not while you are mapping, but when you are choosing what strategy to take, that is important. The performance scores of the user are important while you are choosing a strategy. Like, I'll give you an example of how I use this is, I start with the default setting in Cochlear, default setting of 900 rate ACE. But then if this person is a long-term, having a long-term deafness and deprivation, these people generally say that I'm hearing a loud speech, but then I'm not understanding much of it, and there is a pin pricking like sensation when the sound is loud. When I measure the C levels, they say it's sounding and it's painful, and most of them say it is like a pin prick. Okay, so that is a point when I reduce the rate of stimulation to a great extent. Initially, I used to do it with to 500 and then slowly go up. But now what I've done is 720 and leave them at 720 for some days, and then go to try to get back to 900. For some, they have never been able to come up to 900, but they are very happy and very successful at 720 rate. But then there are some people who have used 720 for some time and then come up to 900. I recently tried the same on two children, and their performances improved drastically with lowering of rate. And I had to use a different stimulation modes because of facial nerve stimulation. getting done in an otosclerotic patient. So there, bipolar mode was quite good enough. So there, I reduced the rate to 250. But then, with a bipolar, I could recover a lot number of channels. So instead of giving them at a high rate but less number of channel, I chose a lower rate with multiple number of channels. So increasing the spectral information over temporal information was the choice that we needed to make.
Mostly it's for the apical electrodes, I think.
No, when it strikes mostly all the electrodes, and facial stimulation. What you are saying is
Ah,
most seen on the not on the top electrode, but around the middle electrodes, upper middle electrodes, about 18, 19 electrode. They are the most notorious for the facial nerve stimulation. With middle, sometimes it is the top electrodes which are more prone.
okay. Pooja has a mostly one experience.
Now I have a question to the surgeons: is why do we see this? Why do we see this mostly on the apical electrodes?
I have Sandan.
Is it because? But then I
Why? So I was asking, why do we see this facial nerve stimulation more in those upper apical electrodes?
Because Sandan, if that's right, if you have a fasciculation or only facial stimulation because of your current, then you have to, I think retrogradely you should go for a review of your CT. Maybe there may be not a dehiscent exact, maybe there is some thin wall partition between the labyrinthine portion of the facial nerve and your basically your electrode is going to have the midturn of the cochlea. That is the place of the most of the apical electrode, and maybe there's a thin dehiscence. That's why you have. That's per my knowledge.
Biswajit, I think the apical turn of the cochlea is in very close relation with the labyrinthine segment of the facial nerve. And the labyrinthine segment of the facial nerve is one of the
uh,
and
thin,
more
that is what that
at that point.
Gautam sir,
Yes.
that is what was my first justification. But then I checked with Amitav sir. Amitav sir said no, that is not the closest part of facial nerve. I am not
The
sure.
closest it does, the nerve sheath is inner there. When we are going for a mastoidectomy,
what he's saying is a horizontal portion. What? Hello, Sandan.
Yeah. Hello.
though not related to this today's subject, I would
Hmm.
like to know from since we have this opportunity, why do some have ground electrode, some have two ground electrodes? What is the reason? What is the advantage, disadvantage?
Having two ground electrodes, it's nothing but it gives a larger surface area for the current to be dissipated, the stimulated current to be dissipated. So the dissipation can be quicker, it can be more efficient. That is the logic of having an extra ground electrode. And sometimes again, like in the implant body, if it's a backup, so it also acts as a backup in case if the one of the ground electrode is not working, we still have a backup. I think Cochlear uses ground electrode. I'm not sure if any other manufacturer uses. So does AB use ground electrode? Like
Yeah,
extra.
yeah. Extra cochlear electrode is there for all users. The thing is, for say the spatially different electrodes were important for good recording of NRTs actually. Now, for a recording of NRT, if two spatially differently located electrodes are used, then you get the best recordings, avoiding the stimulus artifact. And that is why Cochlear's NRTs are the most efficient among all other competitors. And the disadvantage of using two different electrodes is that you make it, the hardware becomes more complicated. So that's the disadvantage of having two different monopolar electrodes. The advantage of having one monopolar electrode, as middle and AB users, is that it is simpler hardware usage, and for stimulation you require at least one.
Okay, then. But yeah, nothing. We can
Sandan
conclude the
sir?
session. We can
Hello?
or Rosina. Okay.
Sandan sir, do,
Rajina,
do we use the same coding strategies for children and adults? Is there any different, like, to be used for children and adults?
clinically it is same for children and adults. We don't
Okay.
use it differently.
Okay. And you were discussing about sonic coding strategy, no? Actually, they even I don't have much idea, but then they use Crystallis XDP.
What?
That is the commercial name of
Crystallis
that
XDP.
That's a commercial name, but what is it based on? What is it exactly?
Yeah, we should ask them, but they like it is like it shows in the software also when we do the mapping. No, it shows Crystallis XDP. The strategy they use.
So let's get it from Shivashish. Little information on this. Okay. So
Yes.
homework for Pragya and me.
Okay, then we can conclude it here. I think this is a beautiful Sunday, and thanks, Pragya, for your elaborative talk. And mostly we have to, as a surgeon, you have to go with your talk mostly 2, 3, or 4 times before the all the strategy we can digest. Huh?
Only then it will be comprehensive.
Thank you, sir. Thank you, Dan.
Thank you, sir. Thank you, everyone, for joining.
Bye.